I put this example on the board while we were working on our worksheet, but I'm going to give you guys a video just so you can follow along if you wanted to for this exercise. So we can read through here and we see SAT scores are normally distributed with a mean of 500 and a standard deviation of 100. We now have everything we need to know essentially about this question to get started. We see the SAT Testing Center claims the middle 60% of scores represent the typical or average student. Immediately we see here they have given us a percentage and a location for where that percentage should be. So we could already draw our picture without even reading the rest of this. We pretty much know where this question is going. We have our bell curve centered at 500. We know we want to shade 50% of this curve, or 60% of this curve. So we're going to shade what we think is about 60%, and we're going to do that in the middle. And if we keep reading, students scoring outside this range are either mediocre or advanced students. Find the two test scores representing the middle 60%. So we can tell that we were exactly correct in what we sort of assumed just from the given information. We're looking for these two SAT scores here on either side of 500. Okay, so as soon as we realize that we're looking for test scores and we have a percent, we realize this is an inverse norm question. We're doing the inverse norm. We have the area under the curve, but we want to find out what the cutoffs were. And this is when we have to be a little bit clever. If 60% of our data is in the middle, then we have 40% left over in these two tails, right? Out here and out here. And since these two tails are, oops, I did not mean to disappear my entire curve. Oh God, that got horrible. Since these two tails are symmetric, that means that 40% has to be evenly split between them. So we have 20% on the left tail and 20% in the right tail. So if we want to come to this first cutoff, we can immediately see what percent is to the left, which is what inverse norm wants, right? So 20% of our data is to the left of inverse norm, and then we can input our mean and our standard deviation. That's going to give us what we usually denote as like x1. Just a little subscript of 1 to say it's the first of our x's. The other one is going to be x2. Use inverse norm again. This time we have to be a little more clever when we figure out what percent, oops, I did not mean to just write it down, what percent of data is to the left of that. We're starting with this cutoff. We're dealing with all of this part of the curve. So we have this 60% as well as this 20%. So there's a total of 80% of the data to the left of this particular value. Same mean, same standard deviation. And then we're ready to use our calculator. So we can go into inverse norm, tell it our area is 0.2, and we're looking at 500, 100. So for the first value, we have a 41.8379. That is a lie. 415.8379. And for the second value, I'm going to use that trick I showed you guys in a previous video. If I do second and then the enter button, it brings back what I last typed. And I can just change this 0.2 to a 0.8. So the other side is 584.1621. 584.1621. The nice thing about these two values, if you want to check your work, we can see we could actually erase these two unknown values here. If we type this, put these into our curve, 415.8, 415.8, and 584.2 are equally far away from 50. So that's our 500, which is a good check that we've not done anything wrong. So we have that check that made sense. So if we wanted to just finish this up, we might write the two test scores that represent the middle 60% are 415.8379 and 584.1621. Yeah, so basically anybody within this range are the average or normal typical students. Anybody over here is a mediocre student, and anybody in this range is an advanced student.